Hi, I'm Bradley Kuszmaul. I'm Chief Architect of Tokutek, and we're building a storage engine that does indexing really well. So today I'm going to talk about indexing. There's been several good talks at here and out of the wider conference about indexing. So let me just start with a little example. This is something drawn from iBench, which is a benchmark that basically we developed at Tokutek to try to measure how good a storage engine is at indexing, and then Mark Callahan revised it and implemented it in Python, and then we did some more work on it. So this basically is a table that kind of looks a lot like a TPCH table. There's a bunch of integers, a transaction ID, a date and time, cash register ID, customer ID, product ID, price, and this is basically a fact table. And imagine having a database that's been populated with 1 billion of these rows. So since it's going to be outside of memory on most of the machines that we use, although you certainly could buy a machine today that has that much memory. But all you have to do is bump this up to 2 billion or 4 billion, and it'll be too big to fit in main memory. Now I want to do a simple query on this. I want to find, among all the items in the fact table, I want to find the product IDs where the customer ID equals 50,000. So just what did customer number 50,000 buy? If I perform that query, it comes up with this list of product IDs. And in this case, since those numbers are essentially random, it turns out that it comes close to 10,000 rows. It's 10,014 rows. It took about 11 and a half minutes to run that. And because this table has no indexes at all on it, it took a long time. It had to do a table scan, and it only basically looked at about 14.6 rows per second for the output. The input, it looked at 1 billion rows. The input of that select, it looked at 1 billion rows in 11 minutes. But in terms of the rate at which rows were produced, it's only 14 per second. So if we throw in the obvious index, so if we're trying to find things that match a particular customer ID, the natural thing to do is to add an index on the customer ID. And so we're showing altering the table to add such an index, and then running the same query. And in this case, it ran in just under 6 minutes. So in this case, it's faster. It's twice as fast, but it still seems disappointingly slow. We're only looking at 0.001% of all the data in the database. That index quickly narrows us down, so we're only looking at 10,000 rows out of the billion. And it still takes the time, half as much time as it would take to do an entire table scan. In this case, it's 29 rows per second. So it just doesn't, it's not very satisfying. So the next trick in our repertoire is to add a covering index. Now, so who knows what a covering index is by now? Pretty good. It's like a year ago, fewer. I'll redefine it because there's enough of you who don't know what, you may not remember what it is. So a covering index is just an index where I've thrown in some more values into the key of the index, so that everything that I mentioned in the query is actually in the covering index. So in this case, I changed this index so that it has the customer ID and the product ID. So if I look at this query here, the select product ID from facts where customer ID equals a certain number, only those two columns are mentioned. So I'm just going to throw the customer ID and the product ID in together, even though my where clause is only on the customer ID. So sometimes you end up in a situation like this where you have a key and it's already been unique. You've got so many items in your index that that each row is uniquely determined by the key. Sometimes you still end up wanting to throw more things into the covering index in order to play this trick. So if we've made this into a covering index with this kind of a query, this kind of alter table, then if we run the select statement, it runs much faster. So suddenly, instead of running in 5 minutes, it runs in 1/4 of a second. So that's a huge performance speed up. And this is going to be true on basically any storage engine that has indexing. So it's going to be true for InnoDB or MySim or ours. One interesting thing to notice is the row order came out different. Here the rows actually come out in sorted order. So 0 is the first one and 99 is the last one. If I go back a couple slides, it came out in some random order. So adding this index changes the answer because we didn't specify, and since we didn't specify the order in which the output's supposed to come, that's allowed. I'll explain exactly why that comes out. It kind of falls out of the way the discovering index works. So we've got a database. It's too big to fit in main memory. That's sort of the setup, right? And we want to design indexes and try to design queries and understand what's going on and be able to predict what the performance is. It's really frustrating if you write a query and you thought it was going to run fast and it runs really much slower than you hope. So in order to attack this problem, I'm going to describe a theoretical model for performance, which works pretty well, and then do some analysis with that. And then I'm going to sort of diverge into sort of a discussion of, you might like to maintain a lot of indexes, which ones should you really maintain? And then I'll touch on an example of TPCH and whether solid-state disk makes much difference. So the theoretical model is, in the literature, it's called the disk access model. And so I'm putting on my theory hat here. A lot of the research we did at Tokutek was data structures research, and we try to be scholarly and use words that other people use instead of making up our own names. Mostly we succeed at that. So the disk access model is a fairly simple model. There's a processor, and there's a main memory, and there's a disk. And when we move data back and forth between the main memory and the disk, we move it in blocks of size B. So it's a very simple model. And in this model, what we're going to do is we're going to count up the number of times blocks move from main memory to disk or from disk to main memory. We're not going to worry about how much CPU time it takes to do something or anything else. The only thing we're going to count is the number of block transfers. And this model actually is a pretty good model. This is sort of implicitly the model that's used to analyze B trees. B trees are set up to have a certain block size, and they try to match that block size to this block, to the underlying block size, which is transferred between main memory and disk. So I assert that this model can be used to predict the performance of a query plan. So let me see if I can do it. So here is the analysis for the case where there's no index. I've represented the entire table here. There's a billion rows up there. If you squint your eyes, you can see them in between the ellipses. I've only actually drawn half dozen of them or something. So the first row is transaction ID 1, and I haven't put all the columns in. I've only put the customer ID and the product ID and not the other columns. And so the first several rows are in block number 0, and block number 0 is of size B. So in this case, let me just assume that transactions 1 through 6,044 fit on the first block, and some more transactions fit on block number 1, which is in a slightly different color, and you keep going down, and so this thing's chopped up into these blocks. And there's a billion rows total, and how many blocks are there? Well, the block size is B, so you take a billion and divide it by B, and that's the total number of blocks. So table scan requires how much work in the disk access model? Any guesses? On the bottom. Well, you have to look at all 10 to the 9th over B blocks. So that's, since all we're counting is the number of block transfers, that's the work. It's 10 to the 9th over B, which is presumably adds up to 11 minutes. If you actually work that out, I think it comes out to about 30 milliseconds per block for block sizes that were actually being used here. So now here's an analysis for the case where there's the simple index that doesn't have not a covered index, just the ordinary index. So there's two things going on here. The first is on the right side is the fact table, which is the same thing as it was on the previous slide, except I've sort of done away with the block shading because I'm hoping that you can remember how that works and not get too upset about it. On the right, on the left side is is this index, which has customer ID as the index. So the first item is customer ID 42 and transaction ID 1. It's probably customers that are lower numbered. And eventually there's a whole slew of 10,014 customers, which are customer number 50,000, which corresponds to transaction ID 6044, and then another customer ID, which corresponds to 20480. So you can think of these things. These things are basically pointers. It's the primary key points over to here. So this points to here, and this points to here. And so what this index does is, let's say, well, the first row I'm interested in is 50,000, which is XID of 6044, which is that row, and the next one is that one, and so forth. So we only had to look at 10,014 rows, but they're spread all over the place, right? So in this case, we end up looking at something like 10,014 different blocks, because the chances that two of these things are on the same block is low enough that we can ignore that for this analysis. So 10,014, how does that compare to 10 to the 9th over the block size? Well, if the block size were 1,000,000, then that would be 1,000. So the block size must be 100,000. Does that make sense? Maybe not. So this is going to be a pretty expensive operation. It's touching nearly as many blocks as just doing the original query, which was a table scan. So even though we don't have to look at very many rows, we're still looking at an awful large number of blocks. So the next trick was to use a covering index, and in this case, the advantage of the covering index is that since we threw in the customer ID and the product ID on the index, we don't have to follow those pointers over into the main fact table. We can just construct the list of the 276, 525, 576. It's right there in the index. We can just fetch it out, and MySQL does that just great. And so in this case, the number of block transfers that we have to do is 10,014 divided by B. So if B is 100,000, we only have to do one block transfer to satisfy this whole query instead of 10,000 block transfers. And so that's essentially the reason why these queries run so much faster. Incidentally, this is also because this key is actually this index is actually being sorted first by customer ID and then by product ID. In this case, this is the reason why these product IDs are going to come out in sorted order for this query, whereas before they were coming out in some random order. In this case, they actually come out sorted. So if you're maintaining indexes, which ones should you maintain? And there's a couple problems that show up. One problem is that MySQL only allows you to have 16 columns in an index, and if you're trying to build some good covering indexes, you might find that you want to have a lot more columns in the covering index than you can really have. So which columns should you throw in? Well, at some level, the answer is 16 is too small. You should just make it larger. So one of the things we did in our version is we bumped that number up to 32. It's a factor of 2 better. Yay. Right, 32 columns. But the second thing we did was we defined a little bit of syntax. So our storage engine, when we include it in our version of MySQL, it has a little extra syntax where when we alter table and create an index, we have this keyword clustering. And what that does is it creates an index which includes all of the columns. So it's sorted by, in this case, it's sorted by the customer ID, but every other column is just thrown in whether you need it or not. And you might, is that a good idea or a bad idea? Well, it turns out with our storage engine that works pretty well. And I'll show you why in a minute. So this you can think of as, this is materializing a table sorted in some other order. This is sorting in the order that the index specifies. And then basically, when you have this kind of an index, it covers every possible query because all the columns are just there. So we use this technique for TPCH, and this is one of these things where it's not really TPCH because we added that keyword clustering, and as soon as you change anything in TPCH, it's not TPCH anymore. But this is a question of how can we make queries run fast, not how big a score we can get on this benchmark. So we've been trying to figure out how to make TPCH queries run better in MySQL, and there's several changes that were announced in 5.4 that help. One of the ones we picked on for this study was query 17, which is one of the slowest ones, and we made a clustering index on the part number and the quantity. There's a big warehouse of parts that are being modeled. And basically, what we found was that we could speed things up from running, a particular query ran in 680,000 seconds, which is like a week. And instead it ran in 770 seconds, which is like 12 minutes. So that's a 773 seconds with a 770-fold speed up. That's an interesting coincidence that the square root of the number is so close to this. So we're going to write a little bit more about that experience in our blog later. So now I've defined this clustering index concept. And if you look at the ideas, like I just said, just throw in all the columns and be happy. And you probably don't really want to do that with a lot of storage engines, because especially if you start maintaining a bunch of indexes, you're doing a lot of work, and those insertions become very expensive. And one of the things that we've done is we've developed a new data structure called a fractal tree that speeds up insertions by orders of magnitude. So if you're doing that, so here we have an example where we have n, which is the number of rows, is 1 billion, and let's assume that the block size is 4,096 rows. So you have a situation where the number of memory transfers per operation for a B-tree index, and a B-tree index can be thought of, for example, as InnoDB or MyISAM. Basically, the cost of doing that operation is log of n divided by log of b. So log of n is 30 and log of b is 12, so that's something like 3, but it turns out that a bunch of stuff is in cache. What it comes down to is that if you do a point query with InnoDB, it's going to cost you at least 1 block transfer in most cases. For fractal trees, it's exactly the same. I wrote it in slightly different notation, I'm afraid. So that's log of n over b. Log of n over log b is the same as log base b of n. So it's basically point queries are the same cost. There's really nothing you can do about that because you have to fetch the data from disk. Range queries, which is where you're fetching a range of values, such as in the case where there was that covering index, you have the same kind of performance. It's the size of the result divided by the number of blocks, by the block size. The difference for a fractal tree and a B tree shows up for insertions. Theoretically, a B tree does insertions that cost about the same as a lookup, so it costs at least a disk I/O for every insertion. You can get a little bit of advantage by playing around with insertion buffers like InnoDB does, but it's basically going to cost you about 1 disk I/O per insertion. For fractal trees, the cost of insertion is much lower. It's log of n divided by b instead of divided by log b. If b is 4,000, that turns out to be a really small number. We're talking about log of n is 30 and b is 4,000, so that comes out to 7 thousandths of a disk I/O per insertion. And so that's basically the technical thing that the Tokutek storage engine does that is fast. And this storage engine, it's not a B tree. It's the moral equivalent of a B tree. It implements indexes, but it's a completely different data structure that has these different asymptotic performance bounds. So some of the things that we don't do and I think are still needed if you wanted to make things like the TPCH queries run fast is you need to do some denormalization, so pre-joining, that means pre-joining some columns. We need better multi-dimensional indexing support. So often you find a where clause where you're doing a where on 2 different columns and they're both ranges. So in this case, I'm saying, well, A is between 38 and 42, and B is between 90 and 99. And if I index on A, then I end up not having very good selectivity for B, and if I index on B, I end up not having very good selectivity for A. Partitions can help solve that problem, but they're kind of painful, and they don't really solve the problem correctly. And I would assert that fractal trees can help solve these problems. Let me just conclude with a little performance graph. This is some measurements that were done for us by Percona, and part of the reason we asked Percona to do it is that, for the life of me, I cannot get InnoDB to run as well as they can. And so if I presented a graph that I measured it, and it's not going to be as good as them, then you would all say that I was being an idiot, showing you cooked numbers. So these numbers are done by somebody who's competent. But the lower set of three graphs, the reddish ones, are all InnoDB running the II-bench benchmark, which measures a sustained insertion load with a set of three indexes. The three indexes are essentially random. And the upper three lines are the Tokutek storage engine. And basically, the bottom line here is a RAID, and then the next one is the Intel X25E solid-state disk. And the next one up is the Fusion I/O. And the Fusion I/O curve doesn't go all the way out because the device failed mysteriously, so we're hoping to get another run with a new part. But the thing that's a little surprising to me is I really expected InnoDB to gain some real advantage from the solid-state disk. And it does gain an advantage. For the Intel device, it's perhaps 50% faster, and for the Fusion I/O device, it's nearly 3 times faster. That's at a huge cost. The RAID 10 is $1,000 worth of disks, and there's a terabyte of data there. The Intel device is a 32 gigabyte device and costs $400, so the price per byte is much higher. And the Fusion I/O is a really expensive device. I don't know the exact price, but I heard it's over $10,000 for that. So it doesn't seem like a very good performance trade-off to be spending that kind of money to get these fairly small performance increments. The top numbers are the Tokutek numbers, and we also get some small advantage from the solid-state devices. But basically, the reason we don't get much advantage is that we're nearly CPU bound, and so improving the performance of your I/O system basically doesn't matter. We're running at such a high insertion rate, just processing rows and inserting them is stressing out the client and the MySQL front end and the storage engine, just running flat out, basically.
How many drives are in that array?
Is Vadim here? Does he know the answer to that? Anybody? It was on the order of 5 or 6 drives, I think. But I don't think it was 10 drives. It was at least 5. So, but I don't know how fast those drives are or anything. So sorry, but I don't know that. Okay. So for II-bench, so I can count it up. It's we're looking at 1, 2, 3, 4 integers plus a date plus a floating point number. So I think it's 27 bytes per row is what that adds up to. So if you're inserting little rows, it's easier to be in it's harder to it's harder to get good bandwidth out of a disk drive when you insert little rows. If you were inserting rows that had a megabyte per row, then the disk seek cost would not be important. What would be important is just how fast, what's the bandwidth of the drive to the disk. Any other questions? That's a single X25E. Yeah.
And this is a standard 16K block size build for InnoDB?
Well, it's standard for Percona. Whatever. I think it's a standard. The 16K block size I think is standard for. I don't think they're messing around with that number, but yeah. It's the usual Percona patches for multi-threading and so forth, but I don't think that includes any changes to the data layout.
And for Tokutek?
Well, because we use fractal trees, there's no well-defined block size. Fractal trees are come from a set of research called cache-oblivious algorithms, and there really isn't a block size per se. So effectively, the block size is probably close to a megabyte for ordinary rotating disk, and I don't know how to. I haven't had a chance to analyze it for solid state disks. Yeah. Yes.
Could you please tell a few words about your storage engine, about its state, when it was started, and so on?
Okay.
Is it free or not?
So it's closed source. You can get a down, and it's going to cost money to put it into production. You can get an evaluation copy for free by going to our website at tokutek.com. Tokutek was founded about 2 years ago, and we've been in beta for about a year, and we just announced that the engine is in general availability starting in May. So in a couple weeks it'll be a GA. And it supports transactions, except it doesn't have full durability at this point. It has crash safety. And full durability will be soon forthcoming, but it's not quite ready. So I'm basically done, unless anybody. Who's next? Come up here. And if anybody wants, is there another talk after me?
Yep, coming straight up.
Okay,
Yeah.
so
So,
I don't want to get in the way of the next.